Hi everyone, welcome to the fourth day of the Beyond the Boolean workshop. So our first speaker for the day is Dan Mikulincer, and he's going to talk about stochastic approach for noise stability. So take it away, Dan.
Okay. So hi, good morning. And it's kind of a long title, and it's not really the title which appears in the schedule. But really, the point is to talk about noise stability on the cube, and somehow to go beyond the Boolean cube, and somehow the theme of the workshop. I should say that this is joint work with Ronen Eldan and Prasad Raghavendra, and I think, well, at least Ronen told me he mentioned it briefly in the boot camp you had like 2 or 3 weeks ago. So hopefully I can give a bit more details than what Ronen said. And also it's maybe I should mention that this is a project that originally was initiated in the Simons Institute, so it's nice to talk about it here. Okay, so let's just take a quick outline of what we're going to do. I'm going to quickly recap on noise stability, on the definition, and then mention one of the major motivations to this work, at the form of one of the most well-known theorems in this for those concepts is the majority Stablest theorem. Somehow we found a new proof for that theorem with better quantitative dependencies. Unfortunately, I'm not going to show the entire proof here. I'm just going to show like a proof of a much easier problem, but hopefully it will give like the major ideas. So I'll explain the approach, and then I'll use it to solve like a toy problem. And surprisingly, this toy problem also turns out to be interesting in its own right. And then if I have some time left, I'll say something about majority Stablest. Okay? And feel free to interrupt me at any point. Hopefully everything is mostly self-contained. Right, so noise stability. So to define noise stability on the hypercube, we have the hypercube dimensions, and mu will just be the uniform measure on it for the talk. And we have the noise operators. It's a semigroup of operators parameterized by the noise between 0 and 1, positive for the talk. And it's an operator on functions. It takes a function, returns a new function, and what it does to this new function, well, it takes the original function and it integrates it around the cube with respect to a correlated measure. So here y is a binary string. It is correlated with x with correlation rho. Okay. Basically, it means that y has a product distribution, and at each coordinate, it has rho correlation with x. Okay. Or in other words, it is the unique product measure which has expectation rho of x. Okay, so that's the noise operator. And now noise stability is a property of a function, and we'll think about it as a property for Boolean functions. So you take your function f, you smooth it or you add noise to it by applying the noise operator zero, and you check how correlated they are. Okay, so it's not hard to see that this is a value between 0 and 1, if this is a Boolean function. And well, it measures how noise affects your function. Okay, by adding noise, how much does the value of the function change with respect to the original value it received? Okay, and one way in which I like to think about it is like f is a voting function. The coordinates of the Boolean cubes are votes. Every dimension casts a vote, and you get to decide to make one decision, either yes or no, depending on all the votes you've seen. And noise stability says, well, how much is your voting system susceptible to noise, right? If I allow you to flip some coordinate, can it really change the outcome or not? Right, so here is a very, I think one of the first examples which shows the importance of noise stability for social choice theory. I won't, say too much about the details, but the point is if you use a Boolean function to rank between 3 candidates, so you need to you have 3 candidates, A, B, and C, and you somehow use your Boolean function to rank them, and you want to say, well, A is better than B, and then B is better than C, and of course, A is also better than C, then this is a rational outcome because it's transitive, and an irrational outcome would be something which contradicts. Right, and if you just use a Boolean function to rank 3 candidates and you draw your votes randomly from the cube, then maybe you would get an irrational outcome. And actually, Arrow's paradox tells you that for most functions, you will get an irrational outcome with some probability, and this can be quantified. And this is a theorem of Gilkar, and this can be quantified by the noise stability with some noise level. Okay, so it's a very nice result. Right, and with this perspective, here is a natural question to ask. If we look on all possible Boolean functions and let's normalize it, let's introduce some normalization, just that they're balanced, which means that the expectation is 0. They have equal chance of giving 1 and equal chance of giving -1, and which function maximizes the noise stability. What is the most stable voting system? Which function maximizes the probability to get a rational outcome? And I mean, if you know something about Arrow's paradox, there's only one function which can maximize it. Kind of unfortunate, and this is the dictator. So this has an easy answer. Among all Boolean functions, the dictator, the Boolean function which ignores all the coordinates and just looks at a single coordinate, has the largest noise stability. So, I mean, it's an easy answer. It's easy to describe it. It's also an easy proof. You can simply diagonalize the noise operators. The monomials are the eigenfunctions, and this corresponds to the minimal eigenvalue or non-trivial eigenvalue. But I mean, it's not a very useful fact if you want to design a good voting system, right? In some circles. But the reason it's not a useful fact is that intuitively we'd want to rule out functions which behave like this. So in other words, we want to rule out functions which only depend on a small number of coordinates. So how can we quantify that? We can introduce the maximal influence, right? Here, this stands for the partial derivative of the Boolean function f, partial discrete derivative in direction I. Simply, what happens when you keep all coordinates fixed and you just flip the ith bit? Does the function change values or does not change values? This is a fancy way to write. What is the probability of the function changing value when you just flip the I bit? This is the influence in the ith direction. And the maximal influence, well, is the maximum over all directions. Right? So obviously this has a high influence because whenever you change the first bit, then the value of the function changes. And every function which only depends on a small number of coordinates will also have a high maximal influence. So somehow having a small maximal influence quantifies how high dimensional your function is and how social, like the social benefit of not allowing a small group to decide or a small junta. Right? So now we can refine the question and ask, among all balanced Boolean functions with small maximal influence, which one maximizes the noise stability? Okay. And now the answer is much, much nicer. Both from the function who actually maximizes it, but also from the proof. And this is the majority Stablest theorem of Mossel, O'Donnell, and Oleshkevich from almost 20 years ago. Right, and the statement is that for if you take any balanced Boolean function and you impose the constraint that all the influences are bounded by some parameter kappa, Then the noise stability of F is bounded by some function of the noise plus some error term. And the error term, I mean, it's quantitative and it goes to 0 as kappa goes to 0. But it goes to 0 slowly. And if you take kappa to 0, then this quantity goes to 0. The reason it is called majority is Stablest is that, well, you can look at the majority function. Just to check if you have more ones or more minus ones. If you have more ones, then the sum will be positive. If you have more minus ones, then the sum will be negative. And well, this has no bearing on the outcome, but it should be suggestive. And no, simply by symmetry, a very easy calculation shows that the maximal influence of majority goes to 0 as the dimension increases. It's not surprising. I mean, that's what we would expect. And a slightly, but just slightly more involved calculation using the central limit theorem, because you can see that this converges to a Gaussian, allows you to quantify the noise stability of majority in the limit, right? And in the limit, this is exactly the noise stability of majority, right? which justifies the name majority is Stablest, up to an additive error. You don't. You know, yeah. I mean, since you're taking sine, then it is exactly the same. It should just be suggestive because I wrote here central limit theorem, but it really has no bearing. Any other questions? And maybe I'll sketch really briefly the original proof of majority is Stablest, both because it's so nice and also because it's somehow relevant to what I'm going to say next. So the idea is to reduce everything to Gaussian space. Okay, so in Gaussian space, you can replace the noise semigroup by the Ornstein-Uhlenbeck semigroup. The majority function, which is essentially an indicator of a half space, becomes an indicator of a half space. And then the analog domination of noise stability by of the semigroup by an indicator of a half space is just the isoperimetric inequality in Gaussian space. So that was known for since the 70s, probably. But now we want, so that's a result in Gaussian space. Now we want to reduce things to Gaussian space, and this is the major theorem from the MOO paper. This is the invariance principle. They prove an invariance principle for low-degree polynomials. Basically, if you take any polynomial on the hypercube and you compare the polynomial in Gaussian space, if the polynomial has small maximal influence, it behaves basically the same in Gaussian space and in the hypercube, so long as it has a small degree. Right? So somehow this is, I mean, incompatible with what we had before, because majority or an indicator of a high space is not a low. I mean, every function is a polynomial on the hypercube, but not every function is a low degree polynomial. And in particular, the degree of majority will be much larger than how much the influence decays. Right? So that's not good enough. And the last step is to replace your Boolean function by some smoothing version of it, which is just what you achieve by applying the noise operator. And what the noise operator does, it attenuates the high frequencies, and it essentially makes any high degree or any polynomial into an essentially low degree polynomial. But all you did for the noise stability is simply added more noise. So instead of calculating the noise stability of your original function, you can calculate the noise stability with a slightly higher noise level to the smoothed out version and get some result. And it turns out that the amount of noise you need to add is exactly proportional to the additive error you had. And this is the cause for this additive error. Okay? Which essentially tells you that any proof of majority is Stablest which goes through the invariance principle must incur this error.
So the quantitative bottleneck is the quantitative aspects of invariance?
Yes.
essentially degree is supposed to be exponential? Or...
It's supposed to be polynomial, I think.
And then the inference will be kappa, and then this is, but like the degree is essentially 1 over epsilon.
The degree is you're saying for 3. Yeah.
Yeah. So the degree essentially becomes 1 over epsilon, and then the 2 to the degree becomes proportional to some small power of kappa. I think it's just
Sorry.
Yeah.
Okay, so I mean that's the proof. I mean, it was super influential for many reasons, many neighboring fields, and what I'm not going to discuss any of the applications, but one thing which you might notice here is that this goes to 0 very slowly. You might want to get a better quantitative dependency in the theorem, even though that I should be honest, for most applications which are asymptotic, you're happy with anything which is little over 1. Okay. And basically what we proved is a quantitative version of majority is Stablest, and it can replace here the sublogarithmic dependence with a polynomial dependence. And essentially, the dependence we get is kappa 1 minus rho times some small constant. And up to that small constant, for some noise levels, this is optimal. And otherwise, it's exactly the same, just the noise level changed. And one way to describe the difference of our proof, and this is what I want to discuss later on from the original proof, is that in some sense, the original proof looks at the noise stability of F, perturbs it slightly further, and then looks at the noise stability of the smoothed out version of F. So in some sense, you're looking at the noise stability as a function of rho, right? You have some expectation. This is a function of rho. And you're asking how much does this function of rho evolve like when you increase rho by a bit? And what we did, we kind of refined this point of view. And when we said, let's find some stochastic process which gives this function as a measurement. And then let's study the path of this stochastic process. So you get a lot more information. Then when you take expectation, well, you already know so much that you get a trivial inequality once you take an expectation, right? So basically, instead of proving an inequality at the level of the expectation, we prove an inequality in the level of the process itself, a process which is parameterized by the noise level, then we can simply take expectations. Right? So somehow we get a finer control, and we get to bypass the invariance principle, which is the nice thing here. And right, we actually use an Ito process to do it, which allows us to use stochastic analysis to analyze it. And a nice byproduct of our proof is that we constructed a new Martingale way to embed the hypercube as a Brownian motion. So, introduction, let me explain the approach. So, okay. Maybe before I say something about the approach. So we have a function on the hypercube. And I said I'm going to realize the function as some Brownian motion. But this is defined on the hypercube, on the discrete cube. The Brownian motion is a continuous thing. So we need to find a way to extend this from the Boolean cube to go beyond the Boolean cube. See what I did there? And to go to the continuous cube. And so there are many, many ways to extend the function from the Boolean cube to the continuous cube. But since we want to work with a Brownian motion, we want to work with a Martingale specifically, there is one canonical way to do it in this case, and this is to take the harmonic extension, and you can describe it in many different ways. But the easiest way to describe it, you have a function from the Boolean cube. It's a polynomial, so you can write it as a polynomial, x1, x3, plus x2. Then you can forget that those are Boolean variables and simply treat them as continuous variables.
So we'd like to call it inside the Boolean cube.
Inside the Boolean?
We thought initially we thought to have three workshops: inside, beyond, and.
This also works beyond, right? This also goes beyond the Boolean cube. We won't do it. But we should. So that's the easiest way to define it. Like the harder way, it solves the Dirichlet problem on the hypercube. The ad hoc way to define it is for an inner function in the solid cube, right? So if x is a Boolean string, when you multiply it by rho, you get something within the cube. Then you simply define it as the noise operator of f applied to that function, right? In some sense, instead of integrating something over some correlated vector in the cube, you simply evaluate some extension in the interior of the cube. So this is the ad hoc definition. And here is the observation now. Let's define a new measure on the solid cube. Basically the uniform measure on the hypercube, but a dilated version of it. And then what happens for noise stability? Noise stability is the correlation of f with its noisy version, but its noisy version is just an evaluation of f of its extension, right? So I'm going to identify f and its extension inside an interior point of the cube. Now, turns out, well, this is a semigroup, it's a self-adjoint semigroup. So you can take one square root rho of here and move it to here. This is a fact. So this is simply an equality. But now, what happens here? We're simply evaluating the harmonic extension of f against itself. So it's no longer, it's no longer a correlation, it's an L2 norm, but not with respect to the uniform measure on the Boolean cube, but with respect to the uniform measure on some dilated cube, and that depends on the noise level. Right? So this is completely tautologies, but we'll simply rewrote the noise stability of f as an L2 norm with respect to some other measure. And this suggests a way to maybe try and generalize the definition of noise stability is let's take any measure on -1, 1, right? And let's define the noise stability of f with respect to that measure as, take the product measure of nu. Nu is some measure on -1, 1. Anyway, this is a measure on -1, 1. It's a discrete measure. So take its product and calculate the noise stability of f with respect to that new, calculate the L2 norm of f with respect to this new measure. And this seems like we've created a new thing here because there's a lot of flexibility in choosing this measure new. But it turns out that nothing special happened. It's an easy proof just by taking orthogonal decomposition over L2. And basically, when we write the noise stability with respect to an arbitrary measure of nu, of f, it simply reduces to the original measure of noise stability, but the noise level is just the variance of nu, right? So here the variance of nu is rho. So the variance of this measure is rho, and this will be true for any other measure. Okay, so again, everything here are tautologies. I haven't really said anything. I've just rewritten the same thing in like 3 different ways. But now, we get a strategy from that. Right? Because now, what would be the idea? Let's find a sequence of measures, a path of measures, or a stochastic process, and calculate the noise stability with respect to that stochastic process. And as long as the variance of the process starts from 0 and goes all the way to 1, for any intermediate value, we will get something. Right? And then we'll simply need to analyze that process. So here is a process. Right? It's an Ito process, it's a Martingale. Here B is a Brownian motion in the cube, it starts from 0. And xt is an Ito process, you simply take the Brownian motion and you re-normalize its variance at every step. So sigma here is a matrix. You take it as a diagonal matrix. When you take it as a diagonal matrix, you are scaling each coordinate separately. So the coordinates of this process are independent.
How many dimensions does the Brownian motion have?
N. So the dimension of the cube. It's simply going to be a process in the solid cube. And the idea is that it will be a martingale. It will stop on the vertices of the discrete cube. So at time infinity, it will be uniformly distributed on the cube. So the idea is to take the Boolean cube and embed it into Rn, and somehow take the measure, the uniform measure on it, and embed it into the path of the Brownian motion. So here sigma t is a diagonal matrix. Every coordinate depends only on the ith entry of the ith diagonal entry depends only on the ith entry of the process, right? So everything really is independent. And what happens here? Basically, you check whether your coordinate approaches a facet. And the closer it is to a facet, the slower that coordinate moves. Right? The closer it is to 1, the smaller this is. The closer this is to, the closer this is to 1, the slower it moves, or the closer it is to -1.
How did you know to use this particular formula? Sorry, how did you guess this particular formula?
A lot of trial and error. But I will explain why in a second.
But would this work with other slowdown?
No, I will explain why. I mean, you can always take a time change and then do the analysis on the time change space, but somehow this is canonical in the following sense, which is irrelevant to the proof, but somehow it explains why this process makes sense. Is if you measure the entropy of the process, it is the unique process in which the entropy decays linearly.
Yes.
Constant rate of decay.
I missed Puya's talk yesterday, but he was talking about polarizing random walks, right? So this is also some kind of slowdown.
Yes. But not the same.
Okay. Yeah.
Yeah. So there are some properties of that process which you like. I'll say one in a second. And really, it's the other properties which matter. But let's start with something very simple. Right, so we can now look at a measure which is the law of one coordinate at time t. So at time 0, I mean, it's a delta measure at 0 because the process starts from 0. It has variance 0. It's a martingale. You can see that it can never leave the Boolean cube because once you reach a facet, you stop. And well, you won't reach actually a facet before time infinity, but that doesn't really matter. But at time infinity, because it's a martingale, every coordinate still has expectation 0. It is it's a product measure, so at time infinity, it is uniform on the cube, which means that the variance of t at time infinity is 1. And at every intermediate time, it interpolates between 0 and 1. You can actually write a formula for it, right? 1 minus something which decays exponentially with t. I mean, it's a calculation to prove that you can simply use Ito's formula to write what is the second moment of x, get some differential equation and calculate that. That won't really matter for anything. But here are some nice facts. So if you look at the terminal point of the path, which is just uniformly distributed on -1, 1, or on the cube, and you condition on everything you've seen up to time t. And this is a uniform, sorry, this is a random measure. You can define yt to have this random law. So at every time t, xt is just the expectation of this random law, which doesn't, I mean, that doesn't really say anything. It just says that this is a martingale. Right? When you take expectation of a martingale, you get what you've conditioned on. But the nice thing is that if you want to ask what is the covariance of your random vector, then this is exactly the matrix sigma t. So at every point, you re-normalize by the amount of variance you have left until you reach the end of the path. We call it a re-normalized Brownian motion. And now here is the point. If we take now any Boolean function f, we extend it harmonically on the solid cube, well, we get an harmonic function. When you apply an harmonic function to a martingale, you get a martingale. So let's call this martingale NT. We get some martingale on the interval -1, 1, and you can analyze its path. Well, and you can ask, what is the noise stability of f? Well, with respect to some noise level, just the variance of the process here. This is exactly the identity we had before. It's the L2 norm of f with respect to nu t, right? So you simply take f, evaluate it on the random vector xt. That's the L2 norm here, and t is just the martingale. And yes, the multilinear is an easy way to say harmonic. It would be true for any harmonic function, but those are the only. And in stochastic calculus, like the nice way to say L2 norm here is the quadratic variation of the martingale. But I mean, if you're not comfortable with Ito processes, then you can simply think about the L2 norm. And what do we do in the proof? So here f is an arbitrary Boolean function. We take another martingale, mt, to represent the noise stability of majority, because nt represents the noise stability of the Boolean function f. And then what we do, we prove an inequality in the level of path. Right? We prove that there is some coupling between n and m, such that the quadratic variation of the square of m dominates the square of n, almost surely. And then, right, when you take an expectation here and when you take an expectation here, obviously you get an inequality for the expectation. So we prove an inequality on the level of path, and then when you take an expectation, you get an inequality for the noise stability. Of course, this is way too much to hope for, right? Because then you would get an exact domination for any Boolean function by the majority. So there's actually some error term we prove here, and it's actually true only up to certain times. And this is why I can present the entire proof.
Can you prove Borel's theorem on this one?
Can you prove Borel's theorem? Simply by the central limit theorem?
No, I'm modifying something here so that you get the Gaussian solution.
I mean, in some sense, our proof uses Borel's theorem, but not in its full strength. So maybe we can bootstrap.
Question before that is, where do you use the fact that the inferences are low? The individual inferences, right?
I'll say that in the end, but I mean, that's a very good question. It would be hard for me to explain. But to get this inequality, the inequality basically, you get here an error term, which depends on the influences. And what we really do, we choose a good direction on the hypercube, on the solid cube. We project those two guys to that random direction, and we apply a central limit theorem in that direction. And then if you have low influences, you can simply use the Racine in dimension 1. So you don't need any sophisticated central limit theorem. But everything depends on having low influences. And the error term you incur will basically be the maximal influence. Any other questions? Okay, so let's use this approach to prove something easy. With theorem. So among all balanced Boolean functions, no other constraints, the dictator maximizes noise stability. Right? So it has a very, very easy proof. You diagonalize the noise operator. Let's do a much harder proof of that. Right? So as before, we have now an arbitrary Boolean function, f, and we have g, which is just the dictator. And somehow we will want to compare the path of nt, which is f applied to that process, to the re-normalized Brownian motion of time t, and well, mt, which is the dictator applied to the same process at time t, and well, we simply look at the first coordinate. Right? And here we will really find the coupling between n and m, such that this is true almost surely, without an error term, because it is really true that the dictator maximizes noise stability among all Boolean functions. So this will be a strict inequality. And so how do you do that? I mean, now we can do some calculations. This will be the only calculations I do. So MT, right? It's some stochastic. It's an Ito process. It's a function. It's a multilinear function applied to an Ito process. You can use Ito's formula to write it, and you know that it's a Martingale, so it will be something times the Brownian motion, some vector times the Brownian motion, and by the chain rule, that vector is just the first derivative of G. So, chain rule is a fancy name for Ito's formula. But G is the dictator, so its first derivative is just one on the first coordinate and zero everything else. So you simply recover the first coordinate of the matrix here, right? Times dbt. Now, when you take the square, or when you take the quadratic variation, you take that prefactor for the Brownian motion and you square it, and you forget about the Brownian motion. This is the basic rule of Ito calculus. Right? So the time derivative of the quadratic variation is the square of the volatility here, which is 1 minus mt squared. Right? This is exactly mt. It's the dictator applied to the process. And very, very hard formula to go from here to here. And the point is that we see that the square of mt satisfies a differential equality. Now, what can we do for the other process, n, which is more arbitrary? Well, we can do the same thing. Write the Ito differential, take the square, right? And you simply get the square of the gradient of f. So this is the gradient of the harmonic extension times the metric sigma t. When you open it up, this is exactly the expression you get, right? So same thing here, but you reweigh every coordinate by the partial derivative of f in that direction. And here is the only point where we use the properties of the process, because this is basically would be true for every other process with a different refractor here, is that you have an almost sure inequality for that quantity, right? This turns out to be just the lower Fourier coefficient with respect to a biased measure, which has exactly this expectation. Right? So by Parseval's inequality, it will be smaller by the L2 norm of the same function. Right? I'm skipping it, but this is just a calculation which you do on the biased cube. And this is the only process which will afford this inequality. Right? So you get that the time derivative of the quadratic variation of n is smaller, well, by 1 minus nt squared. Basically, we get a differential inequality. For mt, we got a differential equality. For nt, we get the same thing as a strict inequality. Okay, it's strict unless this is the dictator. So, I mean, we have those two things. How can we combine them together? Now we want to find the coupling and use this fact to show that this thing is always smaller than this thing. So here is a way to find the coupling. Both nt and mt are one-dimensional martingales. And it's a fact. Any one-dimensional martingale is a stretched Brownian motion. Right, so there exists a Brownian motion. Let's call it W, completely unrelated to the previous Brownian motion, such that if you stop it at a random time, and the random time is exactly the quadratic variation of n, well, you simply get the law of n. Basically, the amount of variance you need before you stop the Brownian motion is basically the variance of the random variable you need to achieve. And this is true for the entire path. So there exists a Brownian motion so that you can embed the entire martingale n into its path. And there exists a Brownian motion, another Brownian motion, so that you can embed the other martingale m into its path. And then you can take the two Brownian motions to be the same. Okay. So basically, this is a way to couple the two martingales in the same probability space. And now, let's reverse roles. Let's fix a time tau and ask, when we look at this Brownian motion W, which is the same here and the same here, this time fixed time tau, how far did n get and how far did m get? Right? So this is the random time for n, t1, and this is the random time for m, t2. Right? And this is just, if you think about it, this is just the inverse of the quadratic variation, and this is the inverse for the quadratic variation of m. But they're inverses, so we want to look at their time derivatives. Right? So we have the inverse function theorem. So the time derivative of that will be 1 over the derivative of the quadratic variation. We've calculated that. We have a differential equality, right? And well, this is again just the Brownian motion at time tau. And for the other process, we have a differential inequality. We're reversing roles here, so the direction of the inequality changes. And when we combine everything together, we see that one random time always evolves smaller at a smaller rate than the other random time, which means that one of them is always smaller than the other. And those are the inverse functions. Right? This is the inverse function of the quadratic variation, which tells us that the quadratic variation of m is always, under this coupling, is always larger than the quadratic variation of n. And again, now we can take an expectation, and we get this proof, very complicated proof of this very simple fact. Okay, but this is basically the idea. You want to prove an almost sure inequality, or at least an inequality in a very high probability. Here we actually could prove an almost sure inequality, and you can simply take expectation and get something. Okay, so that was a complicated proof of an easy fact, but we actually get more. And so now if we take, and this is what we get here, if we take any function phi, which is a convex function, right? So for example, if we take phi to be the square, well, we just proved that the expectation of mt squared is always larger than the expectation of nt squared. But you can take any convex function, right? And if you take any convex function and apply it to mt, well, it's the same as applying the convex function to the Brownian motion at the random time, which is the quadratic variation. And well, we know that this time is always larger than the other time. We proved it. So we can condition on it. And this is a martingale, it's a Brownian motion, right? So when we apply to it a convex function, so simply by Jensen's inequality, we can take everything inside, condition on that thing here, and get phi applied to the Brownian motion at a smaller time. And that smaller time exactly corresponds to n. So not only did we prove that the noise stability of m is always larger than the noise stability of n, we proved that this is also true for any other convex function. Right? And this is not something you can get from diagonalization. And there is one convex function of interest, which is the binary entropy function. Right? And if we apply the binary entropy function into here, we get that this just measures the entropy of the terminal bit, right? F applied to x at time infinity is a random bit, random uniform bit. So it's the conditional entropy when you condition everything on the process up to time t. Then when you use this identity together with this inequality, you get the following result. You can define the mutual information as just the entropy when you clean from it the conditional entropy. And you get it among all Boolean functions, no other constraints. The dictator maximizes the mutual information. So you want to learn something about this random string. You get to do one single measurement. You get to extract one single bit from its terminal point. What is the best bit you can use? Which is the best measurement you can do in order to extract the most information? And just the trivial thing. Just look at the first coordinate. That would give you the most information. And I mean, the thing to compare it to is to the most informative bit conjecture of Tom Courtade, which goes by, and Kumar. And their conjecture is that among all Boolean functions, the dictator maximizes the mutual information in the following sense, right? Again, you have a Boolean, sorry, you have a Boolean string. You can take one measurement, but the difference is that here y is a raw correlated vector of x in the same sense of the noise stability. And here, this is still a correlated version of x, but the correlation structure is basically different. It's not as homogeneous as here. So, I mean, that complicated proof I saw, it basically proves a version of this Kumar-Courtade conjecture with respect to a different noise model. And I mean, this is open for 9 years now, and there have been many results, but it's still open in full generality.
More about what the difference is?
Yeah, I mean, let me, right? The joint law, that's an excellent question. The joint law of x and its raw correlated vector y is simply not the joint law of the terminal point and the intermediate point here.
So let's see the product distribution, right? So every coordinate is on its own.
But they don't have the same, right? They can be different places. So
They can be different correlations.
yeah, exactly. So the point is, if you could force the process to stop at a vertex of an inner cube, and then prove the same thing, then this would exactly give Kumar-Courtade. But for now, we don't know where the process is going to move.
So actually the point inside the cube. Like
It is inside the cube.
So it's not a vertex.
It's not a vertex, but this I mean, you can always round. This is not the this is not the problem. The problem is that there are different locations, different correlations. Right? So it's simply not, it doesn't quantify the noise semigroup in the cube. But it's constructed in a way that the L2 nodes are the same. So any L2 quantity is good for us. Entropy is not an L2 quantity. And here is another point why those two theorems are different. I mean, so not two theorems. The theorem is different from the conjecture. So in some sense, in a very, very vague sense, this is more canonical than this. And why is that? Basically, we have here an inequality for any convex function. So it doesn't have to be L2 and it doesn't have to be entropy. And it's true that if you replace here something which corresponds to the dictator, and here's just any Boolean function, it's not true. There is a convex function, so that there is some Boolean function which dominates the dictator. So this inequality we proved here is too strong to actually prove the full Kumar-Courtade conjecture. So anything we want to prove, we need to change the process somehow. I mean, if it could work, and hope for less. We need to prove a weaker inequality, not something which is almost surely true. 5 minutes left. So I'll say something quick about majority is Stablest. This is what we wanted to prove. And to recap the main ingredients we had from before and how they fit into the new picture now, we have a martingale n, which is the harmonic extension of a Boolean function, now with small influences applied to the process. We'll have a different martingale m to represent the noise stability of majority. Right? So we want it to have an L2 norm, which is this arc sign. We'll prove a differential equality for m, and we'll prove a differential inequality for n. And we'll use the same idea to couple them. Okay, so I mean, here is n. We defined it. We also need to define m. And what we want from m, basically, well, we want it to represent the noise stability of majority. There are infinitely many ways to get such a martingale, but we also want a martingale such that we can compare its path to the martingale we had. I mean, one possibility is to take just majority applied to our process. So this should be xt. So we can take majority applied to the process xt, the same way we took the Boolean function applied to xt. But this is not, I mean, this would depend on the dimension on one hand, so it's not very canonical. On the other hand, it will not give exactly this, because this is only the noise stability of majority in the limit. And on the other hand, really, the reason why majority is Stablest is true is because it's true in Gaussian space. So the idea is to compare everything to Gaussian space. Right? So instead, we take a sort of a limiting object in Gaussian space. And I mean, really, we want something to capture the isoperimetric profile of the Gaussian. This is the reason for majority is Stablest. So this is the isoperimetric profile of the Gaussian, right? It's the inverse CDF or the quantile function composed with its density. It's exactly the surface area of a hyperplane of a given volume, of a given Gaussian volume. And well, we can define MT to simply evolve with a Brownian motion according to this function. Right, so again, this is a function which is 0 on -1 and 1. Sorry, on 0 and 1, but there is, we rescale it. So after rescaling, this will never leave the interval, and it slows down the closer you get to the edges. And I mean, the main idea is that after everything I said, hopefully it's not surprising, is that if you check the quadratic variation, it exactly encodes the noise stability of majority in the limit. So this exactly equals this arc sign, some function of t. And automatically, we get a differential equality for m, right? We simply take the square of that. That's the time derivative of the quadratic variation. So the main technical point is to prove a differential inequality for n. And basically, we prove that if, right, nt is f, the harmonic extension applied to the process at time t, and if f has small influences, then with high probability, this inequality holds. Right? It satisfies, like if you forget about that, it satisfies almost the same equation. So there is some error term which depends on the quadratic variation, but sorry?
High probability of what?
Over the process x. Right? This is a random quantity, and this is a random quantity. And so it's not an almost true equality, but it's enough. It's not an exponential function. But 1 minus exponential function. And when this is polynomial in kappa, so when you integrate it over later on, you get a polynomial error. And I should maybe also say that this is only true up to some stopping time. It can't be true for all times, right? Because basically here, this c times kappa is the maximal influence of the function f, not with respect to the uniform measure, because everything shifts now with time. So it is with respect to the measure on the biased measure on the hypercube, which has expectation x. Right? So the closer you get to a vertex, the less you will be able to expect to have small influences everywhere. Right? But for most times, this is true, and you get this inequality, and this is enough to actually integrate it later on. And as I said earlier, the entire proof relies on writing the quadratic variation as some one-dimensional measurement, basically in the direction of the gradient of f, and then apply a central limit theorem here. This is a vanilla central limit theorem. I'm leaving all the technical stuff for like the last 2 minutes. You get some biased measure on the cube, and you need to prove a central limit theorem for that. I think I'll stop here, and thank you for listening.
Any questions for Dan?
Do these versions of majority of Stablest where you just assume like Fourier coefficient bounds instead of influence bounds? Does this still follow from the proof, or do you have because
if it's essentially all of the big polynomial, if all the high degree frequencies are small?
I think you just need like
So we can argue
L
them and
infinity
then
bound.
you apply them to these.
The high one. So you have small variance, right? So I mean, if all the Fourier coefficients are small, you have a small variance, it's not, you shouldn't compare it to
Small absolute value, not small in.
okay.
Yeah. Usually it reduces to, it just reduces to this statement by
Yeah,
some modularity.
Yes.
So I think that's a question is whether your method gives you the right modularity.
yeah.
Yeah, that's a good question.
No more questions.
I don't see. But maybe.
There's some range of these things for more than like for 3 functions.
You mean like not on the Boolean cube, but like on F3?
I guess.
That's a good question. So somehow, like the point here is that we can embed the cube into Rn and preserve the structure. So for example, you could take F4 and embed it as a product of cubes, and maybe it would work. But yeah, I actually don't know what happens for I don't know what is the correct way to embed other structures in a sensible way into without some comparison. And the point is that this is really a multiplicative subgroup of Rn. That's not true for other units.
The complex roots of unity, products of. So if it's like F3, it's a triangle. And, yeah. There's.
It's still like down some looking at what.
Yeah.
There are no more questions left. Thank Dan again. And we come back in 30 minutes.